Good day, class. Today, I'll discuss to you sample size calculation. And let me share to you my screen. Okay. So, I would like to acknowledge first my friend from St. Luke's. I borrowed the first three slides from her in her lecture on assessing adequacy of the sample size. First three slides were taken from her lecture. Okay, so when should sample size calculation be provided? Sample size calculation is required for quantitative studies like cross-sectional studies, case control studies, cohort studies, clinical trials. So in practically all quantitative studies, sample size calculation is needed. And this may not be required, sample size calculation may not be required for qualitative research with formal qualitative methods such as content analysis, ethnography, and what have you. Qualitative studies don't require sample size calculation. It may not be required for certain preliminary studies. And I would like to explain to you why we don't need to calculate for the sample size for qualitative research. The reason is we don't intend to generalize results from samples to population. You see, in qualitative research, we don't intend to generalize results. It is only in quantitative studies, in quantitative research, that we want to generalize results from samples to population. Remember when I gave you a lecture on sampling methodology, I told you that we normally do not study the whole population. We only study a sample. And based on that, and from the results of that sample, we generalize them, the results, to the target population. And so we intend to generalize results from samples to population. And so we need to calculate for the sample size for quantitative studies because we want to know if the sample size that we calculate can be sufficient to make generalization of our results. And the following must be specified in the sample size section of the proposal for qualitative research, sampling strategy, and sample size. If you want to calculate for the sample size are based on similar published literature. And sample size is tentative and is likely to change through the process of research for, as I said, qualitative research. Now, for feasibility study and pilot study, sample size may not be appropriate. But for pilot studies, we can have this median pilot study sample sizes for 2-arm trials. Okay, if the outcome is dichotomous, okay, so we have 36 per arm and 30 per arm for continuous outcomes or quantitative endpoints. Well, this is just an arbitrary number. You can have more or less, but really for pilot studies, as I said, we don't need to calculate for the sample size. But if you want to calculate, you can have these arbitrary numbers. But as I said, pilot studies don't intend as well to generalize results. And that is why we don't really calculate for the sample size for pilot studies. Now, In the calculation of the sample size has to be calculated during the design phase. I mean, during the protocol making, sample size has to be calculated. And the following formula will depend on, the formula for the sample size will depend on the following parameters. The parameter that you want to estimate, and this parameter that you want to estimate is normally taken from the objective of the study, the type of the research design used, and then the sampling design or the sampling methodology. And I would like to emphasize to you that population size is not considered in the formula, is not considered when we calculate for the sample size. You don't need the population size for you to be able to calculate for the sample size. And that is why I see a lot of people calculating for the sample size, because the population, given this population, you don't need that population for you to be able to calculate for the sample size. Now, some generalization in the sample size calculation: the rarer the condition, the larger the sample size. So if the condition is rare, you need a much larger sample size to be able to detect that condition. Complex data analysis require larger sample size than simple analysis, because you see, you need much larger sample size if you have complex data analysis. For example, when you do multivariate analysis, you need much larger sample size than if you will just do simple analysis. The more heterogeneous the values of the parameter are, the larger the sample size. And heterogeneity of the values is normally seen from the standard deviation of the parameter that you want to estimate. In general, longitudinal studies, meaning those studies that will require follow-up, require a larger sample size than case control or a cross-sectional study. The reason for that is you need to provide a correction factor for non-response or refusal rate or defaulters, attrition. You need to provide for this correction factor. Well, aside from the non-response or refusal rate. So you need, and that's the reason why for longitudinal studies, we need to add another factor in the sample size calculation. Normally, I use 20 to 25%. I add 20 to 25% for longitudinal studies, just in case there will be dropouts. The higher the level of accuracy and the precision desired for the resulting estimates, the larger the sample size. So if you want a more accurate, more precise estimates, you need a much larger sample size, Later on, I'll show to you in the calculation of the sample size that we can actually manipulate the number. If you want, if you, for example, will not be able to attain this much number of sample size, you can, as a matter of fact, make it larger or smaller depending on the level of accuracy or the level of reliability or precision of the sample size. And sample size will be a compromise of the different ends, of the different computed sample sizes and available resources. I just told you a while ago that the sample size can be manipulated. I mean, you can make it large, you can make it smaller, okay, depending on the available resources. The final sample size will depend on the available budget and other resources that will effectively implement the study. So we can make it a little bit lower, but only as much, but only not really very low. There will be the minimum sample size that that is required. You cannot go lower than the minimum, lower than the minimum. And the calculation of the sample size should be based on the objective of the study. And again, not based on the sample size. You see, the reason for this is that we need to know whether the sample size that we calculate can answer validly the objective of the study. And that's the reason why, we need to calculate for the sample size based on the objectives of the study. Now, if you have two objectives or more than one objective, calculation will need to be done for the two specific objectives. If you have two specific objectives, and whichever comes out to be the higher, that will be the final sample size. So let me repeat that. We calculate for the sample size for each objective. If you have two or more objectives, so we calculate for the sample size for each objective, and whichever comes out to be the highest will be the final sample size. And the reason for this is that why one needs to calculate for the sample size, well, based on the objectives of the study, is for one to know, as I said a while ago, whether the sample size calculated is sufficient to answer the objectives of the study. Okay, some clarifications. Sampling methodology is different from sample size calculation. If one collects sample size using total enumeration, meaning you will have to get all subjects that are available, and then sample size will still need to be calculated, because there is a misconception that because sampling methodology will be that sampling methodology that will be used will involve total enumeration, and technically people are saying that that is not a sample anymore, because you will be doing total enumeration, and then they say that sample size calculation is no longer required, and that is a misconception. That's a misconception. The reason for that is, as I said a while ago, sample size has to be calculated based on the objective of the study. Now, and so it can happen that this is the number of sample size that we calculate, and then the available subjects are only this much. That becomes a limitation of the study. You will have to calculate for the sample size based on the objective, and then you say that this is the population size that I only have. So there will be a limitation of the study. Now, just to go back to that concept of people saying that total enumeration is not sample size, is not needed because you are not talking of a sample, because that's total enumeration, that is incorrect. Because really, that will still be a sample, because the total enumeration that you have in a hospital, for example, will only involve people in that particular hospital, but the target population will be much larger than what you have in the hospital. And that is why the total enumeration is really still a sample. And you still want to know whether that sample that we have will sufficiently answer the objective of the study. And that's the reason why, as I said, we need still to calculate for the sample size. Now, okay, I mentioned this issue a while ago. Population size is smaller than the calculated sample size. You can still proceed with the study, but with limitation, as I said. And results from your study can still be used if people do meta-analysis. Or another option is do a pilot study. Do a pilot study if you only have that much number of population. But of course, you cannot do a pilot study if there have been studies before. So it can no longer be a pilot. It can no longer be a pilot study. The study has two objectives. One is descriptive and the other analytic. And the sample population can only fulfill the descriptive objective requirement. You see, between the two objectives, a descriptive objective and an analytic objective, okay, if you will calculate for the sample size for each of these two objectives, the objective that is analytic will necessarily have much larger sample size than the descriptive objective. But we only have this. The issue is that we only have this much number that can only fulfill the descriptive objective. So what we can do is to just make a descriptive objective as the primary objective and the analytic a secondary objective. So it will justify the investigator calculating the sample size based on the primary objective. But of course, I would like to take note of this, that the results from the analytic objective will have some limitations because we won't be able to fulfill the requirement for that analytic objective. Okay, so we have two types of sample size. As a matter of fact, there are many, but I will just zero in on these two types because these two types are the ones that are most often used. Okay, the estimation, that is for for descriptive objective, you are trying to estimate something, and for hypothesis testing, that will be an analytic objective. Now, for estimation, we have estimation of the population mean for quantitative data. We also have estimation of the population proportion for qualitative data. And with estimation, we talk of reliability of the estimate and the maximum allowable error. The higher the reliability, the larger the sample size. 80% is the lowest acceptable reliability. You can't go lower than 80. This is what I was saying. I was telling you a while ago that I said that sample size, the minimum sample size can be only that much. You cannot go lower than what should be the minimum. In this particular instance, if you want to lower your sample size somehow, make your reliability estimate as low as 80%. And then another one, the lower the maximum allowable error, the larger the sample size. The lower the maximum allowable error, the larger the sample size. And for hypothesis testing, we have testing the hypothesis for the difference between two means for quantitative data, and testing the hypothesis for the difference between two proportions for qualitative data. Now, for both sample size estimations, the number of the sample size calculated is multiplied by the number of groups. From the formula that I will be giving you when you calculate for the sample size using the test of hypothesis, okay, the result will be multiplied by the number of groups that you have. You will note that with hypothesis testing, you are comparing two or more groups. So that will be multiplied, the number will be multiplied by the number of groups that you want to compare. Now, with hypothesis testing, we talk of power, alpha error, direction of the hypothesis, whether it is one-tailed or two-tailed. So it is only in hypothesis testing that we talk of power and alpha error. The higher the power, the larger the sample size. And 80% again is the lowest acceptable power. We can't go lower than 80. And the lower the alpha error, the larger the sample size. But of course, the higher alpha error that we normally use is up to 0.1 or 10%. And many times, if you want to put a lower alpha, you can put it at 0.01. 0.01. Well, the alpha error can be 0.01, 0.05, or 0.1. Now, the lower the alpha error, the larger the sample size. And one-tailed alternative hypothesis has much smaller sample size requirement than a two-tailed alternative hypothesis. Okay, so let's talk first of the estimation of the population mean. And this is the formula for the estimation of the population mean. And I won't bother you with the formula. I just showed to you what the formula is. But normally, I don't want you to calculate because there are many calculators. I have, for example, a calculator that will automate the calculation. Well, the n is the sample size, the s squared is the variance, d is the maximum allowable error, and the z is the reliability estimate. As I said, I don't want to belabor on this point, on this formula anymore. And these are just to show to you the different z values that we normally use for the different reliability. For 80% reliability, the z value is 1.29, for 90, 1.64, 95, 1.96, and for 99, 2.58. These are the different z values that we normally use for each corresponding reliability estimate. Now, let's give an example. An ophthalmologist wants to determine the mean baseline central retinal thickness among patients given Avastin. And this is a descriptive objective. Mean baseline central retinal thickness among patients given Avastin. Avastin is normally used by ophthalmologists for macular degeneration. This is an off-label drug. Avastin is a chemotherapeutic drug for colon cancer, but ophthalmologists give Avastin to macular degeneration. They inject it intravitreally. Now, one of the problems they say of Avastin injection of Avastin is that the central retinal thickness will be, there will be thinning of the central retina, and that is the reason why this ophthalmologist wants to determine the mean baseline central retinal thickness, prior to giving this Avastin. Now, as I said, that's a descriptive objective. And to calculate with the sample size, he needs to make an estimate of the maximum allowable error of the mean baseline central retinal thickness. And that's a plus or minus value of the mean estimate. And this plus or minus value, this maximum allowable error, is arbitrarily assigned by the investigator. And he also needs a standard deviation of the baseline central retinal thickness. The standard deviation is based on previous studies, If he likes his estimate to be plus or minus 30 units of the true value, so the maximum allowable error is plus or minus 30 units with a reliability of 95%, and a standard deviation of 176 taken from previous study, and normally we say who the author is and when that publication, that study, that research was published, and then we can calculate how many patients will be needed in the study. So we can use the formula, but as I said, we can use the automated program now that will calculate the sample size very quickly for us. Now, let's go to the next estimation, the estimation of the population proportion for quantitative variables that is also dichotomous. So qualitative, I should say, qualitative variable, and is dichotomous. And this is the formula. This is the formula for the sample size calculation for estimation of the population proportion. Again, the sample size is the n, and then the z, the reliability estimates, and then the proportion q. P is the estimate of the true proportion, and Q is just 1 minus P, and then the D square is the maximum allowable error, as we said a while ago. Now, let's give an example. A biochemist wishes to estimate the prevalence of zinc deficiency among diabetic patients. So again, this is a descriptive objective. Now, To calculate for the sample size, if that is the objective of the study, he needs to get the prevalence of zinc deficiency among diabetic patients in previous studies. Suppose prevalence in a related study is 10%, and of course, again, you need to provide an author who said where you got the 10%, and the desired position or the maximum allowable error is plus or minus 3%, and a reliability of 95%, he can calculate how many participants will be included in the study. Okay, now, I just would like to tell you, class, that between the two estimation of the population mean, estimation of the population proportion, the one that will yield much larger sample size will be the estimation of the population proportions. So when we estimate population proportion, qualitative variables, we will have much larger sample size than if we estimate the population mean. So that if, for example, your objective, you have two objectives. One objective is calculating for the population proportion for qualitative variable, and another one estimating a quantitative variable, that which will yield the larger sample size will be estimation of the population proportion. Now, let's go to the next type, test of hypothesis. And the factors to be considered in the computation of the sample size for the test of hypothesis will be this alpha error, that's denoted by z sub 1 minus alpha, the beta error, and that's also the power of the test. The effect size will be the difference between the two means, mean sub 1 and the mean sub 2, the two means, or the two proportions, proportion sub 1, proportion sub 2. Later on, we'll be explaining this to you. And the type of the alternative hypothesis, whether it's one-tailed or two-tailed, and the variability as measured by the standard deviation for quantitative variable, and the proportion for qualitative variable. Okay, so let's go first to the test of hypothesis for quantitative variables, and we compare means. Okay, so the first is the test of hypothesis for the difference between two means. So we compare two means. Again, this is the formula, but I won't bother you with the formula. The power, the alpha error, I should say, the power of the test. This one is the standard deviation, sigma, and then the mean difference or the effect size. The effect size is actually the mean difference, estimated difference that is of clinical significance. So the difference should be of clinical significance, because if the difference is much too small, it may not be clinically significant. The sample size will be very, very large. Now, but the difference will also be just enough, not very, very large, because if the difference, if the effect size is much too large, again, the sample size that you calculate will be small. Okay, let's go to an example, a test of hypothesis for the difference between two means. An ophthalmologist wants to determine if there is a difference in the percent reduction of central retinal thickness between those patients given less than 4 injections of Avastin after 1 month of treatment and those given 4 or more. So this ophthalmologist, actually the same ophthalmologist that I talked about a while ago, wanted now to determine if there is a difference in the percent reduction of the central retinal thickness. I told you a while ago that Avastin can make the central retina thin. And so there will be a reduction of the central retinal thickness among those patients given Avastin. Now, this ophthalmologist wants to know if there is a difference, or the difference in the percent reduction of those given less than 4 injections after 1 month of treatment. So 1 month of treatment, 4 injections versus those given 4 or more injections. Now, so things that he needs, okay, well, this alpha error is again assigned by the investigator. The power of the test is assigned by investigator. The effect size, well, this can be taken from the previous study. If you have two means that you can get from previous study, mean percent reduction among those given less than four injections of Avastin, and the mean reduction, mu sub 2 mean reduction among those given 4 or more injections of Avastin. And the difference will be between these two means. For example, the difference is 10%. The difference is 10%. That is the effect size. And then the type of alternative hypothesis is two-tailed, meaning you're not saying the two-tailed alternative hypothesis, you're not saying that one has more reduction than the other. But of course, you can use one-tailed if you hypothesize that giving 4 or more will have much larger reduction than giving less than 4. But then you say one-tailed. But in this particular instance, they used the two-tailed, and then the standard deviation for both groups is 10. Okay, now, and then we can calculate for the sample size using a calculator, as I said. And then lastly, test of hypothesis for qualitative variables. So we compare proportions. We compare proportions because we are talking now of qualitative variables. And this again, the formula. This is the formula. We have the same alpha error. We have the same power of the test. And then just this, the P is the population proportion for the first proportion, second proportion, and then we normally get the P bar. The P bar will just be the average of the two proportions. Okay, so that's the P bar. And of course, the Q will be 1 minus P. 1 minus P. And this one, P sub 1 minus P sub 2 is the effect size, the difference in the two proportion, the effect size. Okay. Let me give an example. A hospital administrator wants to compare the incidence of neonatal infections among premature babies with one group of babies breastfed fully and the other bottle-fed. Okay, so two groups of babies, one bottle-fed and one breastfed fully. So incidence of neonatal infection. Okay, and these are the things that he needs. Okay, again, the alpha error is arbitrarily assigned by the investigator. Power of the test is 90, again, arbitrarily assigned by the investigator. And incidence of neonatal infection among premature babies is 25% based on previous study. And if, for example, I gave this example many years ago when there was not much study yet on this. Okay, anyway, breastfeeding is hypothesized to reduce the incidence to 15%. So the effect size is 10%. If you don't have studies, for example, on these comparison of these two groups, no, you only have one study, for example, for one group, and for the other group, you don't have a study, you can hypothesize as this was made. So breastfeeding is hypothesized to reduce the incidence to 15%. So the effect size is 10%. 25 minus 15 is 10%. Okay, and so he will be able to then type of alternative hypothesis one tail, and then sample size required this much using the calculator. Anyway, now, so let me give you an example of the write-up, how the sample size calculation is written. Now, suppose this is the objective of the study, the last test of hypothesis, the example that I gave. Okay, suppose the objective of the study is to compare the incidence of neonatal infections among premature babies with one group of babies breastfed fully and the other bottle-fed. So that's the objective of the study. And this is how you make a write-up of the sample size calculation. Sample size was calculated based on the comparison of the incidence of neonatal infections among breastfed premature babies versus bottle-fed babies. Suppose neonatal infections in bottle-fed premature babies is 25%, and I normally say you provide the author for that. So I didn't provide it anymore, but you need to provide who the author is, and then the year, open close parentheses. And among breastfed babies, we hypothesize that incidence be reduced to 15% with an alpha error of 5%, power of 90%, and a one-tailed alternative hypothesis. Sample size required is 271 per group, or as I said, we normally multiply this by the number of groups. Since you have two groups, one bottle-fed and then another one breastfed. So two groups, we multiply this 271 by 2, and then there will be 542 groups. Now, just a note prior to the continuation of the write-up, if we do multivariate analysis, we normally add 10% up to 25% per variable that you want to control. So with multivariate analysis, there are more variables that we need to control. So depending on the number of variables that we need to control, we add 10 up to 25% per variable to be controlled. And so if the sample size calculated is 542 and we want to control for 4 more variables, we control for 4 more variables in the analysis, we add 25% times 4 or 100% in the sample size, and the final sample size becomes 1084. 542 times 2, because this is 100%, so times 2, and the final sample size is 1084. So how do you put this in writing? This is just a note. So continuation of the write-up, controlling for 4 more variables in the analysis, and with an additional 25% for each variable controlled, final sample size is 1084. Okay, so that is the complete write-up of the sample size calculation for this particular objective. Okay, one final note. Okay, with estimation of the population mean and the population proportion, the higher the sample size, the better. Much larger sample size will yield more accurate results than smaller sample size. So with estimation, the larger the sample size, the better, the better. But of course, you need to look into some ethical considerations when you get more sample size than is necessary. For example, based on the sample size calculation, estimation of the population proportion, for example, and the sample size required calculated, for example, is 386, just as an example, 386, that is the required sample size. Now, getting more participants than 386 will yield much more accurate results, except that there can be some problems related to ethics, because ethics will say, for example, that why will you recruit more if this is only the required sample size? People that you recruit are not necessary anymore, because with this much number, the required sample size you will be able to answer the objective of the study. And so why recruit more? You understand? So why do you need to recruit more patients when it is no longer, when more patients will no longer be necessary? And that's the reason why sometimes we don't recruit more if we only have this much. I mean, if the sample size that we calculate is only this much, you understand, because of some ethical issues related to that. But of course, if you are talking of data, collected retrospectively, you can get more than what is required, because as I said, more accurate, higher sample size will yield more accurate results. And there won't be any problem as far as ethics is concerned, because you are collecting retrospective data anyway. Okay, But with test of hypothesis for the difference in the population mean and the population proportion, just an appropriate sample size or a little bit higher is needed. Much larger sample size will give results that will be statistically significant but may not be clinically significant. Meaning, if this with test of hypothesis, a while ago I told you that with test, with population, with estimation, larger sample size, more accurate results. But with test of hypothesis, when we are talking of test of hypothesis, difference in the population mean or population proportion, much larger sample size than is required. If you get much more than is required. So for example, you need 1,000 population, 1,000 population sample size, that is the required sample size, and then you get 10,000, 20,000, or more, 30,000 population, and then that will be much higher than what is required. Results will be statistically significant, but may not be clinically significant. And that's the reason why we need just enough sample size for a test of hypothesis, not very large, not very small. Because with very, very small sample size, the opposite will apply, meaning difference with much lower sample size, there may be a clinically significant difference, but it may not be statistically significant. Now, let me just explain to you what is meant by clinically significant. For example, if you want to look into the blood pressure, systolic blood pressure of a particular drug for hypertension, for the reduction of systolic pressure, okay, and if, for example, the difference between two drugs, one given an experimental drug versus the standard drug, for example, and if the sample size is very, very large, you can have a statistically significant difference. For example, the difference of 118 and 119 millimeters mercury for systolic blood pressure will still be statistically significant. But the difference between 119 and 118 is not clinically significant. And yet, with much larger sample size, the difference can be statistically significant. So what is my message? With test of hypothesis for the difference in the population mean or population proportion, just enough, just what is required. But for estimation of the population proportion or mean, much larger sample size, more accurate results. I think that will be the end of my lecture. Thank you for listening.